How do you guys like the lights in here? Let's go with off. Too dark? Too dark. So that's the next level. Okay. So thanks so much, Andrew, for that introduction. Thanks for having me. I've had a really great day visiting here and talking with all the faculty and students and postdocs. What a wonderful place to do astronomy. So I'm going to be presenting very new results, actually. This is a brand new talk that I have a chance to give for the first time here. And even though these are new results, I think all the main results that I'm going to show were published in the last year or so. This is a journey that I've been on for a long time. I realized when I was preparing this talk that I started working on M-dwarfs and their planets when I was an undergrad. And I won't say how long that's been since I was an undergrad, but it's been a while. And so really, ever since then, I've always kind of come back to this question of what are the nature of M-dwarfs and their planetary systems. And the reason I've maintained an abiding interest in these objects, well, there's a few reasons. Well, one is because they're the most common kind of star in our galaxy. If you just take a random sample of 100 stars in our solar neighborhood, you find that three of every four of those stars is an M-dwarf type star. If it weren't for our own existence around a G-type star, I'm not sure astronomers would be super interested in G-type stars. They would probably be more interested in the M-dwarf type stars. So they're very numerous, but they have some observational advantages as well that make them particularly compelling, right? We want to understand how planetary systems form and evolve around these kinds of stars because they're extremely numerous. But also, we have the chance to study smaller and cooler kinds of planets that for a given level of measurement precision than we otherwise would. So here's a classic plot of how the circumstellar liquid water habitable zone depends on the mass of the star. Since smaller stars are less luminous, the habitable zone is closer in. And they actually, for the lowest mass stars, they're at orbital separations where they're amenable to study with radial velocities and transit techniques. The transit probability for objects within about 0.1 AU of a mass star is reasonably high, so we can expect to find and characterize those objects. The small size of these objects also makes them particularly advantageous for transits and radial velocities. For a given signal size, you can find smaller planets. Radial velocity and transit signals all are inversely proportional to either the mass or the radius of the star. So radial velocity signal goes up for smaller mass stars. For habitable zone stars, habitable zone planets that are closer in, the smaller semi-major axis further increases the radial velocity signal. Transit depth goes up, transit probability is higher, and transit frequency is higher. So these stars offer a lot of just really exciting opportunities for a given level of measurement precision. You can find and study cooler and smaller planets. The focus of this talk is on the small planets, really sub-Neptune and smaller sized planets. From the Kepler mission in the 2010s, we learned that M-dwarf type stars have lots of small planets. The integrated frequency of planets of sizes up to about 4 times the size of the Earth within even orbital periods of 50 days approaches 1 planet for every star. So these stars are numerous. The signals are relatively large. Every star nearly has a planet. So it's a really ripe hunting ground for finding these kinds of objects and studying them. Now, M-dwarfs don't just come with advantages, they have their own challenges, and that's why it's been this long journey that I've been on to try to find and study small planets around these small stars. Well, the first thing to say is that they're intrinsically faint, so you just generally need a bigger telescope to do this work. Another more subtle point is that these stars present a very different kind of planet formation and evolution environment than sun-like stars do. So that's an interesting challenge, but also an opportunity. In the particular context of this talk, where in the second half I'll be talking about the presence or absence of atmospheres of these planets, M-dwarfs emit a higher fraction of high-energy radiation to their bolometric radiation, and that's more likely to strip atmospheres of planets. So compared to sun-like stars, the existence of atmospheres around rocky planets around these stars is less guaranteed. From the measurement standpoint, our observations can often be contaminated by stellar activity. these stars evolve more slowly as they approach and exist on the main sequence. They have a different interior structure. The latest type M dwarfs are fully convective. So all that means is they can be magnetically more active. And so that it can introduce jitter into radial velocity measurements. It can also lead to spectral contamination of transmission spectroscopy when you try to study the atmosphere. And then finally, the stars themselves as planet hosts are sometimes difficult to precisely and accurately measure their fundamental properties. They have cooler photospheres that host molecules. They have internal structures that are different than some-like stars. And so with the radial velocity and transit technique, which are the techniques that I'm using and talking about today, we measure planets relative to their stars. And so we only know the planets as well as we know the stars. And so actually you'll see in a later part of this talk how even the accuracy at which we make our stellar parameter measurements and determinations can impact our interpretation of our measurements. So I'm going to talk about using three major facilities to study small planets around these small stars. One of these facilities is the TESS mission. It's an all-sky, nearly all-sky transiting planet survey mission that launched about 5-6 years ago. It surveyed nearly the entire sky for transiting planet candidates around the brightest stars. So the information that we get from TESS is we use that to find the planets that we're looking at. We're interested in transiting planets and combining that with radial velocities. So we get planet candidates from TESS, and then if those are real planets, then TESS gives us the radii of those planets. We're also using a little telescope called the JWST, which you may have heard about. The powerful thing about JWST in this game is that it allows us to study the atmospheres of planets in more detail and study planets that we weren't able to study using previous facilities. This is enabled by JWST's very large collecting area, its presence in space, and a very stable platform. But especially for transiting planet atmosphere studies, the very wide spectroscopic wavelength coverage of all of its different instrument modes and its access to features from a lot of different chemical species is a really big advance over the previous facilities. The thing that links these two NASA big facilities, space telescopes together in this talk is my own group's instrument called MAROON-X. So MAROON-X is a new radial velocity spectrograph that my team built. And it's this sort of unifying thing because it is the thing that turns TESS planet candidates into real planets. It's confirming those objects. It's measuring the masses of those objects. So we have the mass and radius. We have the density and thus the bulk composition. We know what kind of planet we're talking about. And it enables atmospheric characterization because you know what kind of planet you're talking about. You maybe need to know the timing of the secondary eclipse. You've got the mass for the surface gravity, so you can interpret atmospheric observations. So TESS and JWST are well known, but MAROON-X is maybe a little bit less well known. So I'm going to spend a few minutes talking about it. So as I said, it's a radial velocity spectrograph. It's a extreme precision radial velocity spectrograph. It's kind of the new vernacular for these instruments. It's a highly stable, high resolution spectrograph. It's optimized, we built it and optimized it for M dwarf type stars. A little bit of historical note, the last time I gave a talk here was in 2011, and I was saying, hey, we're going to build this kind of instrument, and it took us about 10 years, and we actually did it, so that's pretty exciting. It's always good to call your shot. But so we built this instrument, and it was commissioned in late 2019. We started science operations in May 2020. Those of you who can cast your mind back to May 2020, you might remember that's the middle of the early days of the COVID-19 pandemic. We were super lucky to get the instrument installed on the telescope before that started, and we started doing remote observations during the pandemic, and we've continued ever since. We had a laser frequency comb funded by the Moore Foundation installed in 2023. It's been open for community use for the last few years, and it's a transition instrument in the sense that we currently run the instrument, but Gemini is going to be taking it over the next couple of years. The key thing about MAROON-X is it was designed for extreme precision radial velocities of red stars. We've achieved radial velocity precisions down to 30 centimeters per second, and we've done precise radial velocities, down to stars with visual magnitudes as faint as 19. Since starting the instrument, we've had 31 science papers submitted or published, and we've managed to get one paper each in Nature and Science. So a little bit about the secret sauce of MAROON-X. MAROON-X is this next generation of instruments built on the concept of the HARPS instrument that was built by the Geneva Observatory and ESO. So it's a stabilized instrument. It sits in a vacuum tank in a climate-controlled chamber. It's fed by fiber optics from the back of the telescope. It sits down here in the Pier lab of the telescope, well away and climate-controlled and stabilized. But some of the new things that we did to make the instrument work even better than the previous generation of stabilized instruments like HARPS, we did things like using novel fiber optic shapes, including octagonal shaped fibers to improve the image stabilization. So comparing octagonal fibers to circular fibers, just seeing how the image smoothness depends there on the output face of the fiber. You can see those octagonal fibers are a lot more uniform, so that's better for radial velocity stability. We use octagonal fibers and D-shaped fibers, both of which have advantages in terms of their stability. We built some novel gizmos to keep the instrument small. We started to do slicing in the pupil plane to reduce the size of the instrument. If you might recall from your basic astronomy instrumentation, as the size of the telescope gets bigger, your high-resolution spectrograph needs to get comparatively bigger unless you make your slit size smaller. One way to make the slit size smaller is slice in the image plane of the pupil plane. We do the latter because we think that's more stable. So this is just a small little diagram of the gizmo that we use. It's based on a curved lenslet array that we feed the pupil image into, split that up into 3, and then put those pupil images, re-image them, and then put them down a rectangular fiber, feeding that ultimately into the spectrograph. Wavelength calibration is essential. We have a laser frequency comb that's operational, but our primary calibration source currently is based on a Fabry-Perot etalon that's stabilized. So this is just a picture of what our little etalon looks like, fed by single mode fibers, stuffed in a stainless steel vacuum tank, and passively controlled the temperature. Ultimately, what the MAROON-X data format looks like is something you might be familiar with from high-res. It looks like a classic Echellogram, but for each Echelle order, we actually get 5 different spectra. We have a sky fiber. We have we get 3 slices of our science, and then we have our simultaneous calibration fed by the etalon. You can see the etalon gives a very nice comb of evenly distributed, even intensity lines to allow us to do simultaneous calibration during the night. In terms of radial velocity performance, the instrument has broken some new ground. Here's an example of an observation, not of an M-dwarf type star yet that we optimized the instrument for, but from a typical sun-like star that has a giant planet in a eccentric orbit. And the key thing here is that this is a great test of an instrument's precision because all other planets should have been swept away by the existence of this giant planet on an eccentric orbit. The star is also relatively old, so it's relatively quiet. So you can see we observe this star regularly as a standard in calibration, so you can see our performance compared to other state-of-the-art instruments there. So over 900 days, we took regular observations, and we get RMS values in our 2 different arms below 70 centimeters per second. This is without any correction for stellar activity. It's just the removal of the known eccentric planet. If we had been observing this star and it didn't have this giant planet and we were looking for planets, we would have been sensitive to signals below a meter per second, confidently detected out to about 900 days. So this is showing the instrument has a really good level of sensitivity that's a significant improvement on previous generation of instruments. For M-dwarfs, this is where we're really shining. Our red optical sensitivity is perfect for these M-dwarf type stars. So this is one of our first science results from the instrument where we measured the mass of an 3 Earth mass planet with radial velocity, so the transiting planet discovered by TESS. And this is the phase-folded orbit, and you can compare our data with the previous generation of instruments. The key thing here is, this is a 3 Earth mass planet that we measured extremely easily. The velocity semi-amplitude is measured to a precision of 10 centimeters per second. There's no trending for stellar activity. And if you just bend the blue and red arms of MAROON-X together over 30 minutes, you get this magic 30 centimeters per second number. We've done a lot of other science with MAROON-X. We can push towards fainter objects, which is pretty cool. So here's a measurement of the Roster-McLaughlin or spin orbit alignment for a hot Jupiter orbiting an M dwarf. Here's the radial velocity orbit of that, which we didn't measure. Here's the thing we did measure, which is when the planet transits, you get this velocity anomaly that allows you to see if there's an alignment between the angle of the planet's orbit and the rotational axis of the star. So this is a pretty typical kind of measurement, but this is a 15th magnitude M dwarf, which is something that wouldn't have been able to reach before. An even more extreme case is the Roster-McLaughlin effect on the very famous TRAPPIST-1 star. This is nearly 19th magnitude M dwarf, and we measured that for a couple of the planets in the system, and you can see it's a bit ratty, but we're doing a few meters per second precision on a 19th magnitude star. It's pretty crazy, to be honest. MAROON-X has also been useful. I think my thing just crashed, excuse me. Of course it did. Well, let's try to relaunch. This is the last problem we're going to have in this presentation, those of you who are here a little bit earlier. One of the other things that MAROON-X can be used for is this emerging area of high-resolution spectroscopy of actually planets' atmospheres. So this is a measurement of a number of chemical species in the atmosphere of ultra-hot Jupiter, WASP-76. This is time resolution of Fe plus and Fe lines during the transit of a planet. So we're actually not just summing all the data during transit, but mapping the velocity of these lines during the transit. That allows you to detect chemical inhomogeneities in the planet's atmospheres and the wind speeds of the atmospheres. So all this is to say is a vast array of science, really exciting science being done. It's a general purpose high resolution spectrograph. But back to the main thread here, which is radial velocities of M dwarf type stars. The main reason we built this instrument was to perform this survey, which is being led by my senior graduate student, Madison Brady, who's on the postdoc market this year. She's titled this survey the Humdrum Survey, and I won't pretend to remember what the acronym means. But the thing to take away is that this is a survey looking at TESS M dwarf planets, all TESS M dwarf planets within 30 parsecs observable for Mauna Kea. So the idea is a volume-limited survey that allows us not just to, for individual planets, measure masses and radii, constrain bulk composition, and so forth, but to do that in a systematic way that it gives us statistical power. And so we aimed in this survey with relative mass areas to 20% or better. We achieved 10% for most, and we can even achieve 5% for good targets, with our objectives of getting statistical constraints on the mass-radius relationship, the mass function of M dwarf planets, detect additional planets, and enable JWST atmospheric characterization. The red points here on the plot on the right are our humdrum surveyed planets in the context of the TESS planet candidates. So you can see here by targeting planets orbiting M dwarfs and the nearby M dwarfs, we're typically reaching the smallest and coolest kind of planets that TESS has been able to find. As an example of measuring masses for these kinds of planets, this is the most recent one that we've published. This is a single object study. This is a 1.3 Earth mass planet with a roughly 1 meter per second velocity semi-amplitudes. You can see it very clearly here. One of the things that we're doing here is we're trying to get the mass function of planets that orbit M dwarf. So we're trying to find all the planets and systems where we found at least one transiting planet. So we identify non-transiting planets as well. Those are just as interesting to us. The planet that is transiting, we can put it on a mass radius diagram, and you see it there. This planet, which is a fairly anonymous kind of planet, is the second lowest mass planet, transiting planet with a mass measured from radial velocities. So you can see there it's sitting on the frontier of low mass, small objects populating the mass radius diagram. It's remarkable to say that a 1 meter per second signal is pretty easy for us. That's a really exciting thing. The challenging thing actually was the periods of these days. Andrew, you might notice that that's not an easy period. Anything near an integer is tough to get the phase coverage of. So anyway, that's one example just to give you a flavor of the kinds of measurements that we're making and what we're trying to do. The survey in total is starting to reach its conclusion, at least phase one of its conclusion, which is covering a couple of years of TESS observations. So we have precise measurements of planet masses down in this regime, and so this is the raw measurements for the objects in our sample. Number of planets versus planet mass. You can see it's predominantly smaller planets. Since we're doing a volume limited survey, we're able to de-bias our survey. But to do that, we need a model for the completeness of TESS. We have done that, and this is just a map of the typical sensitivity of TESS in the regime that we're looking at. So if you plot period in days and planet size, it's easier for TESS to find larger planets on shorter period orbits. And a lot of the planets that we're studying are sort of on the edge of TESS's sensitivity. So we can take this completeness map and apply it and basically invert our raw planet mass measurements into an occurrence frequency, which we do here on the right. So this is one of the main results coming out of Madison's program to date. And I think it's pretty cool because I see two things in this plot. The obvious thing is that objects that are less massive, approaching 2 and 1 times the mass of the Earth, are much more abundant than larger planets. So that's pretty exciting. I also starting to see a separation here between objects that are, say, 6 to 9 times the mass of the Earth and the smaller planets. Put in the context of the mass radius diagram, I have a suspicion that these are the intrinsic sub-Neptunes or super-Earths that retain or lose their hydrogen envelopes. And these are the things that are intrinsically objects born rocky. So we're starting to see a separation there, which I think is pretty interesting and may have ramifications for planet formation. The TESS completeness on its own, separate from the MAROON-X survey, actually gives us a chance to look at planet frequency as a function of the radius of the star. So the M-dwarf stellar category is actually pretty broad, covering about a factor of 6 in stellar radius and stellar mass. And so it's not really a uniform monolithic stellar category. There's a big change in stellar properties across this category, and there could be changes in planet frequency. Planet frequency in terms of planet radii as a function of stellar radius or mass had been quantified with Kepler about 10 years ago, but that was mostly focused on earlier M-dwarf type stars. TESS's sensitivity across the whole sky allows us to push that towards later type M-dwarfs. And so what I'm showing here in black are the raw TESS planet candidates in our sample. We're just looking at numbers of planets as a function of stellar radii. And then applying our model for TESS's completeness, we can assume 3 different kinds of planet frequency relationships. The yellow or gold line is the classic result from Dressing and Charbonneau in 2013, where we've summed over our parameter space of sensitivity. It gives around 2.5 planets per star in this orbital period range and planet size range that we're sensitive to. There had been some preliminary suggestions from a more detailed study of the Kepler data that planet frequency increased dramatically to smaller stellar radii. So that's Hard Degree and Ullman, 2019, suggesting that. And if you look at those compared, gone through our TESS sensitivity calculation, you'll see that neither of them actually reproduce what's going on for the smallest M-dwarfs. They're all pretty good down to about 0.3, 0.35 stellar radii, but the number of TESS planets that have been found, even accounting for TESS's completeness, is lower than we would expect from those results. And so Madison came up with the idea of fitting this Gaussian-looking planet frequency curve and running that through the simulation. And that provides a great match to the data. You may think, well, that's a kind of crazy model of planet frequency to apply, but it's actually well motivated from pebble accretion models, where you have, the thing that's going on here is you have disk mass, protoplanetary disk mass decreasing with stellar radius. For the larger stars with higher disk mass, you create fewer larger planets that gobble up all the material and mess up dynamically the formation of other objects. So you end up with fewer planets. As you go to smaller disk mass in that model, you're able to form more smaller planets and fewer larger planets. So planet frequency seems to increase. But at a certain point, you reach sort of a sweet spot in ideal planet mass, protoplanetary disk mass, to create the most number of planets. And then it starts decreasing as you further decrease the mass of the protoplanetary disk. So this is a result that kind of went a little bit unheralded last year, but I think it's really important. Planet frequency increases and then decreases over the period range we're sensitive to, which is up to about 15 days. So very close in orbital periods, but it disagrees with the extrapolation of the Kepler results. Okay, back to the humdrum survey and masses and radii together. This is the mass radius diagram for all the planets in our sample compared to some theoretical models. Planets up here are Neptune size, so probably Neptune-like objects. And the plot on the right zooms into this part of the diagram for the small planets. So you can see here populations emerging. You've got the classic sub-Neptune type planets. You've got rocky planets here consistent with Earth-like composition. And you do have intermediate size and density planets that are potentially water worlds. Looking at just the rocky planets here, okay, homing in on those that seem to be consistent with 100% solid composition, you can do interior structure models on those to try to derive the core mass fraction in these objects. So how big is the nickel iron core versus silicate mantle in these objects? And you can get relative frequency for those objects. And really interestingly, it peaks near Earth-like core mass fraction, but slightly lower than that. So this is statistical distribution. Individual objects are more or less consistent with the Earth, but it's pretty similar to the Earth, but slightly, potentially underdense compared to the Earth. So I think that's pretty interesting. Water worlds. This is a class of planets that has, definitions vary, but a few percent or more volatiles in the form of water, ice, and things like that, hypothesized to exist and then kind of forgotten after the Kepler radius valley was discovered. There's been reinvigorated interest in these objects based on a paper from a few years ago by my postdoc Raphael Luque and his PhD advisor Heinrich Paye. They proposed the existence of water worlds for M-dwarfs based on a similar sort of mass radius diagram uniform analysis. These objects here, they're consistent with a few tens of percent water mass fraction in these objects. This is a heterogeneous sample of M-dwarf type planets. We have a volume limited survey, so we're able to put statistical constraints on the frequencies of those objects. So I've drawn some dashed lines here to highlight those objects. So they seem to have a comparable frequency to the sub-Neptune type planets in this period range for M-dwarf type stars. They're vastly outnumbered by the smaller planets, which we have larger numbers of them in terms of the raw sample, and then when we debias the sample, we suggest there's even more of those objects, but they do seem to exist. If you look at their color coding in terms of their equilibrium temperatures, you see that they are typically cooler objects, which makes sense from a planet formation standpoint that would have icy planetesimals or pebbles or even migrating embryos moving in from further out in the system and not getting parked as close to their host stars as more refractory dominated objects would be. Okay, so conclusions on the first part of the talk on the humdrum survey, measuring masses and radii of these planets for a volume limited survey. So we think the frequency of close-in planets peaks near a stellar radius of about 0.35 solar masses. Planet frequency increases towards stars that are smaller than the sun, but then reaches a maximum. The smallest stars have fewer planets than expected from the Kepler extrapolations. Super-Earth type planets, terrestrial planets, orbiting M-dwarfs have essentially uniform bulk compositions consistent with that of the Earth, perhaps with a slight underdensity. There may be a bimodal distribution of small planet masses around M-dwarf with one peak near 5 to 7 Earth masses, the other peak at about 1 Earth mass or lower. Completeness right now is limiting us to saying where that peak is. Terrestrial Earth mass planets are much more common than larger planets. And then volatile-rich water worlds do seem to exist, although they're not as common as terrestrial planets are. Okay, Switching gears now to what we've learned about the atmospheres of these planets, I'm going to talk about JWST observations now, looking for atmospheres. And when I say looking for atmospheres, that's what I really mean. We're looking for the presence of atmospheres. Have these objects been able to form and retain atmospheres? And that retaining atmospheres is really the key question for M-dwarfs. Like I said at the beginning of the talk, M-dwarfs have a higher incidence, they have higher amounts of XUV or high energy radiation compared to the bolometric irradiation, and that's more easily driving atmospheric escape from these objects. The atmospheric retention question is sort of the existential question for rocky planets orbiting stars, whether they can be habitable or not, ultimately. This question can be framed in terms of this idea called the cosmic shoreline, which was proposed by Kevin Zonla and David Catling a few years ago. The cosmic shoreline is a phenomenological or empirical observation of objects in the solar system being separated into two classes, those with and without atmospheres. And you can make a couple of different versions of this plot. One of them is sort of the naive version, which is just insolation or total irradiation versus escape velocity. Escape velocity is how easily the planet can hold on to an atmosphere. Insolation is how much energy is the planet getting that would drive off an atmosphere. This is a little bit of a confusogram, but the idea here is that there's a sort of diagonal line running through this plot that would separate objects that are too highly irradiated or have too low surface gravity to retain atmospheres versus those that have high surface gravities or low irradiation and can maintain atmospheres. M-dwarfs, in the context of this plot, we have found planets that should be, from the standpoint of just their bolometric irradiation, on the good side of the cosmic shoreline. A classic example is the planet orbiting our nearest neighbor, Proxima Centauri b, nominally in the star's habitable zone because it receives about 65% the total bolometric irradiation that the Earth does. However, there's a version of the cosmic shoreline plot that changes the y-axis for cumulative XUV irradiation, the thing that may drive atmospheric escape more easily than bolometric irradiation. Because Proxima Centauri b orbits a late M-dwarf and only receives 60% of the bolometric irradiation, it actually receives currently 60 times the amount of XUV irradiation that the Earth does. And over its history, it's received something like 16 times the cumulative amount of XUV irradiation that the Earth has from the sun. So where does Proxima Centauri b sit on this shoreline? Well, we can't answer that question now because this kind of planet is a little bit out of reach with our current facilities. But we can test this idea of the cosmic shoreline by looking at planets that are a little more irradiated, that are transiting their host stars, and for which we can get their atmospheric characteristics from JWST. Since JWST launched, there's been an active area of research. The technique that I have been using, my group has been using, is focused on measuring the thermal emission of the planets, measured at secondary eclipse. This is a sort of more indirect way at getting at atmospheres, but it's a great way of testing for the presence of atmospheres of planets where your naive expectation would be that they don't have atmospheres. It's great for that null hypothesis test. The idea here is that bare space rocks are dark. They have low albedos. They absorb all of the incident radiation and they heat up and re-radiate that to space. And we can measure that at secondary eclipse. If a planet has an atmosphere, then the atmosphere would be either more reflective than a bare rock, and or it could transport heat from the day side to the night side. The point being that bare rocks should have their maximum secondary eclipse depth compared to the expectation from energy balance, whereas planets that have atmospheres would have shallower eclipses. This can be illustrated here in this diagram where you've got an object with no atmosphere and what its phase curve would look like in its secondary eclipse versus something with a thick atmosphere that's maybe got a higher albedo and is transporting heat to the night side. So you could go measure the whole phase curve, and people have done that. But if you can make the simplifying assumption that bare rocks are dark, which there are geophysical reasons why you can, then you can just do this observation at the secondary eclipse. That tells you something already about the dayside temperature, which you can interpret in the context of planets having atmospheres or not. Here's a simulation of what the kind of measurement would look like. We have models with a range of albedos and emissivities, so those give a range of bare rock surfaces. and then our expectation for atmospheres with different compositions and different thicknesses. And this is what JWST could measure. This is what we simulated JWST could measure before its launch in terms of a secondary eclipse for a classic kind of example of this class of planets. The advantages of secondary eclipses compared to the alternative of transmission spectroscopy, if you're familiar with that, is that, for one, there's almost no sensitivity to stellar activity. Transmission spectroscopy has to contend with the planet crossing the disk of the star if the disk of the star has any sort of heterogeneity to it due to spots and plage and other kinds of activity-related effects, then that will be imprinted on the stellar, on the transmission spectrum of the planet, and you'll have to try to remove that, and that's quite challenging. Transmission spectroscopy can also be impacted by aerosols. Those of you who've known any of the work I've done about 10 years ago know that flat spectra from transmission observations can be a thing, and they can be caused by aerosols. Aerosols are good for secondary eclipses because they would typically make the planet more reflective. Okay, and they would only exist in the presence of atmospheres. That would make the secondary eclipse shallower and be an indicator of atmospheres. But they can make transmission spectra flat, and you can have a degeneracy in your interpretation. Is it a bare rock with a flat spectrum, or is it a planet with just high aerosols? You don't know. And then also, if you do secondary eclipse observations and you're doing spectroscopy, you do have the potential for detecting spectral features, just like with transmission spectroscopy. Okay, so in the pre-JWST era, this technique was applied a couple of times using Spitzer-Irach photometry to really very hot planets, and in the JWST era using 15-micron filter photometry with MIRI is applied to 2 of the planets in the TRAPPIST-1 system. All of these results are indicative of planets with no atmospheres. Our group has also done some observations as well. I'm going to walk you through the details for one of these planets and then show a summary, a synthesis of all the observations that have been obtained to date. So this is an observation that was done by my graduate student, Chao Xu, who observed this planet GJ 1132b, it's not so important in its name, using the MIRI LRS instrument. LRS is a low-resolution spectrometer, takes data between 5 and 12 microns. One of the things we do in transiting planets when we get spectra is, first of all, just sum it all up and measure a so-called white light curve. This is what the data look like, and it's not much to see, but it is an 8 sigma detection of the secondary eclipse right at phase 0.5, so right at the phase where we expect the planet to be going behind the star. A cool thing about this secondary eclipse is actually there's a clever way to use it to refine the properties of the host star that are needed for the interpretation. I don't have time to go into the details of that, but it's a pretty nifty thing that's turned out to be quite important. So here are what the data look like. FP over F star, planet-to-star flux ratio, or secondary eclipse depth, is a function of wavelength. It's spectroscopy, so we can get spectra, and we can also sum it up there in our white light curve. The thing to take away here is we have different ways to reduce the data. These are really quite sensitive measurements out of a few hundred parts per million, right? Not something that JWST actually was really designed to do, but we're doing it anyway. So we try different reduction codes and reduction strategies to make sure they agree. And they do, and that's good. Not much to see here, but you might look at the little inset. I've labeled here the maximum possible eclipse depth in gray, and there should be a shaded region that's not showing up on the plot. But basically, all the different reductions and ways of analyzing the data already agree with the maximum possible eclipse depth for this planet. So that's already a hint that the planet may not have an atmosphere. Now, getting more quantitative, the way that we've been quantifying this difference from the maximum possible secondary eclipse depth was this parameter we're cleverly calling R, which just stands for ratio. I didn't think it would take off, but it did. But it's the ratio of the measured dayside temperature to the maximum temperature. And so for this planet, we're getting 0.95 plus or minus 0.04. So 1 would be maximum possible dayside temperature. So you can see it's consistent with that. If we use energy balance arguments and the amount of heat transport expected for atmospheres of about 1 bar, like our own Earth's atmosphere, or thicker, then that's already inconsistent with that. Those atmospheres should be transporting more heat from the day side to the night side and making the day side look colder than it is. We can also put our constraints using the secondary eclipse depth into a map of heat redistribution efficiency, which in this case we've parameterized to vary between 0 and 1, and the bond albedo, which tells you how much of the bolometric irradiation is being reflected and absorbed. So our median constraints, since we only have one data point and two parameters, we're doing a cut through this parameter space, are here. Venus would look like here in the diagram, Earth would be here, airless bodies are down here. Small bond albedo, low heat redistribution, okay? So you can see our observations are consistent with the airless bodies of the solar system and inconsistent at high confidence with solar system bodies that have thicker atmospheres. If we assume the planet has no atmosphere, then we get a constraint on the bound albedo, which is pretty cool, of about 0.2 plus or minus, say, 0.1. That's from the white light curve, so integrating all the light together. We have spectra, and we can compare those to atmospheric models, which we're showing here. So these are the spectra now reframed in terms of the brightness temperature at a different wavelength. So how hot would a black body of comparable size would need to be to give off the amount of flux that we get from the planet. So we're getting the data here, and the spectra are a bit ratty, but you can see that over our bandpass, there are spectroscopic features from water and from CO2 that we would expect to see if the planet had an atmosphere. We can turn these into more rigorous constraints shown here, which plot goodness of fit versus surface pressure. So what you should do is take your favorite kind of atmospheric model of a terrestrial planet and go and identify the color and go from left to right and see where it starts to become inconsistent with the data. You may favor, for a highly irradiated planet, a Venus-like atmosphere mostly made of CO2. You can see here very thin CO2 atmospheres are marginally consistent with the data, but as soon as you start increasing the atmospheric pressure, they become inconsistent. A couple of things are happening. CO2 atmospheres are actually pretty reflective, so that's working against them. That's making the day side colder. We have CO2 absorption features that we don't see, and then as you get to about 1 bar, you start to have a significant amount of heat transport. You can do the same for a variety of other models. The takeaways are here on the right. For atmospheres that have at least 1% water, that's kind of like the Earth's atmosphere, atmospheres thicker than about 1 bar are ruled out. Even small amounts of CO2, very thin atmospheres, are ruled out. And super trace amounts of water or CO2 in a Venus thickness atmosphere are ruled out. Now, so we're probably seeing a bare surface on this planet. It does not have a significant atmosphere. So what about the surface composition? Can we make lemonade out of these lemons? And the answer is, well, kind of. We can. This is again, the brightness temperature spectrum of the planet that we measured compared to different theoretical models for what we expect on this planet. It's not super constraining in terms of the mineralogy of the surface, unfortunately. The spectral features for those different surfaces are not very strong, and their emissivities are not very different in this wavelength range. Okay, so with secondary eclipses, we put strong constraints in the presence of an atmosphere on this planet. I said it's better for this kind of object than transmission spectroscopy. Just to prove that's the case, I show here the state-of-the-art transmission spectra that are in the literature for this object. You can see here a lot of bumps and wiggles, and you may be tempted to try to fit those with features, and that's kind of the challenge of low signal-to-noise transmission spectroscopy, is you'll get bumps and wiggles, and you don't know whether it's the star, you don't know whether it's some molecule you didn't expect. The takeaway here is that the secondary eclipse is a lot more constraining for this planet. It's also a lot more constraining for a variety of planets. So here's a sort of collage of the observations that my group has made or been involved in. So this is the secondary eclipse of one planet. Former Caltech grad student Michael Zhang measured a phase curve of another planet. My postdoc Rafael Luque has measured a phase curve, and this is just the day-side spectrum of another planet, and we were involved in the data reduction for even another planet. All of these observations in total do not paint a picture of M-dwarf planets in this temperature range having atmospheres. But now that we're accumulating a decent number of measurements between ourselves and also those results that exist in the literature, is there something that we can say about the population level? So these are results that are being prepared by UChicago grad student Brandon Coy and Space Telescope postdoc Jae-Geog Lee. This paper should appear on arXiv, might be next week. So if you're aficionado, then you can check this out. But we've tried to take a look at the sum total of these JWST thermal emission and some Spitzer observations, what they mean for the presence of atmospheres and whether they may be statistical trends. So we're plotting our very cleverly named R parameter, which is the ratio, I bet you don't remember that, versus the irradiation temperature of the object. So GJ1132b, here's the one I told you about. I showed you this one, and here's all the others. So they fit some models to this purely without any physics to see if there's any sort of trend. And so the models with the least amount of physics are like these models because an R value greater than 1 is kind of unphysical. There are probably some reasons why you could get that, why the brightness temperature of a planet's day side is higher than the maximum, but they're not great reasons. So any trend that goes higher than 1 is maybe not great, but these are, technically the best fit. The one that I'm most interested in is this more subtle one, this kind of dotted line that has kind of a step function here. Because if you just said, okay, what if below some level of planet irradiation, you start having atmospheres? You start being able to retain atmospheres. That's kind of what you'd expect. It would kind of expect it to sort of turn on, meaning this R value would go down. And so that step function is a better fit to the data than just a single R value for all the objects. I'm not sure what that means. It's not super statistically significant. And if you look at individual data sets that are driving this, you can squint and kind of see different things. But this is pointing the way forward, I think, in terms of what we'd like to do. Now that we've established this technique, we'd like to build up a sample of these measurements and try to make sense of them on a statistical level. That's the story of astronomy, after all. If we look at these objects and the constraints on atmospheric pressure, this is what we get. So Earth-like composition atmospheres are typically having to be thinner than 1 bar. Venus-like compositions dominated by CO2 have to be even thinner. So if there are atmospheres turning on at lower irradiation, they're still quite thin. They're not thick Venus-like atmospheres. What's probably going on more than anything is that we're just seeing bare surfaces on these objects. And that is really exciting, actually, because since you're seeing surfaces, you can start to do geology of rocky extrasolar planets, which is maybe not something I would have expected to be doing with my life years ago. In terms of trends that we would expect, you can plot this R parameter versus the irradiation and do a couple of different kinds of models here. I think a takeaway is that the data are already suggestive that fresh surfaces that are either feldspathic or ultramafic are inconsistent with the data. Lower albedo surfaces could be fresh. Basaltic is probably the prime candidate. That's consistent with the data. But there are other things that matter, and that's super interesting. So, for example, the grain size actually measures in terms of the albedo emissivity of the planet. Larger grain sizes make the planet less reflective, and smaller grain sizes are more reflective. And so there could be a trend arising from that. Space weathering may be the dominant source of what's altering the surfaces of these objects. Space weathering is a physical and chemical alteration that typically darkens surfaces. And so space weathering of ultramafic and feldspathic surfaces actually could explain the sort of subtle trend seen in the data. There's a couple of different kinds of space weathering. It depends on how much iron is in the rock and what kind of material that you're weathering. There's no specific takeaway here other than these are the kinds of physical processes that we can now probe since we're pretty sure we're seeing the surfaces of these objects. Now, going back to my original framing for this part of the talk, which is we want to look for atmospheres. We want to put this in terms of the cosmic shoreline. We want to see where it is that planets have to be to have atmospheres and what are the controlling factors. There's 3 flavors of the cosmic shoreline. I've shown 2 so far. So this is total irradiation. This is cumulative XUV irradiation. There's also another version that it considers median impact velocity. And you can see where all these objects that we've measured lie on this diagram. I think we can say with high confidence already that simple bolometric irradiation is not the controlling factor. It's something else. XUV irradiation is probably important, but we shouldn't also discount this impact velocity parameter either, because we simply don't know. So this is where we're at now. Some of these measurements shown here are not the best and could probably be reshot. But we are a little bit limited in the number of targets. So you may think, well, this is a great technique for distinguishing between atmospheres. It's relatively inexpensive. All you have to do is observe a secondary eclipse or two. Why don't we just push this thing to the limit? Why don't we push down in terms of cumulative XUV irradiation or installation or impact velocity? Well, the problem is that planet-to-star flux ratio is a strong function of planet temperature, which then depends on the irradiation. If you go down in irradiation, the temperature goes down, the planet-to-star flux ratio goes down, and the number of eclipses and the amount of time you have to spend to do this goes way up. To make a long story short, if you plot the known M-dwarf planets in this cosmic shoreline plot and you scale the point sizes by the signal to noise, you can see that we've already observed a lot of the best targets. There are a few more that could be observed, and we could get higher signal to noise for some of these, but if we want to push in towards the cosmic shoreline and beyond, this technique is not the one that's going to do it, unfortunately. So what do we want to do? Well, here I'll just make a simple statement that I think ultimately to push past where we think the cosmic shoreline is for M-dwarf rocky planets, we have to go back to transmission spectroscopy despite all of its flaws, and we have to try to solve those things. But in the meantime, as we continue to use thermal emission measurements, we can learn more about statistical trends. And we also have the option of pushing towards hotter objects, which don't tell us anything about what kinds of planets might be habitable, but can tell us about how planetary surfaces start to evaporate. And so there's ongoing programs that will populate the rightmost part of this diagram and fill in this space and tell us more about how planetary surfaces melt and outgas, which I think is also pretty cool. So conclusions for the final part of the talk. Our JWST thermal emission measurements of rocky M-dwarf planets have revealed no robust evidence of atmospheres. In many cases, they've placed stringent limits on the presence. So that's disappointing. Thermal emission has been very powerful, and for planets with equilibrium temperatures above about 350 Kelvin, it's been more sensitive than transmission spectroscopy. We're making lemonade out of lemons. The lack of atmospheres opens up the opportunity to study rocky planet surfaces. Temperate planets are still best studied probably with transmission spectroscopy, and we do need more targets. So that feeds back into the first part of the talk, finding planets, measuring their masses. So that's the end of the main thing I wanted to talk about, and I'm going to leave with just a single slide, which is a teaser for some results that are going on. This is observations of a famous nearby M-dwarf using MAROON-X, where we've been able to find 4 planets, all sub-Earth mass, around this star. I'm showing just the smallest, hardest to find planet, where it's not identified either robustly in our MAROON-X data or with data from the similar espresso instrument, but together the evidence is extremely high. And I just want to highlight the velocity seeming amplitude of this planet, 20 centimeters per second, and the mass of this object, minimum mass of about 20% the mass of the Earth. You can see here in the periodogram, this planet is confidently detected in the periodogram. And so this is, I think, a really exciting result showing the future potential of EPRVs around nearby stars. MAROON-X, KPF, and the other instruments that are there have a bright future. There was a lot of skepticism when I gave my talk in 2011 about the future of RVs and stellar jitter and whatnot. This result is just by removing the harmonic of the stellar rotation period from the data and nothing else. With just these measurements, we identify 4 sub-Earth mass planets around this nearby star that you know the name of, and we could push this even further. So I'll finish my talk here, and I'd be happy to take questions. Thanks a lot.
Okay, it may not be enough to be the important
Mhm.
key, but my question has to do with observation.
Yeah, so spectroscopy, that is a nice thing about that, is it's not super sensitive to total pressure. Even just of gas will give you a signal in transmission. It really depends on the scale height, but the planet's atmosphere is a tenth of a bar or 10 bars. It doesn't make that much of a difference. So if you wanted to do that, then transmission spectroscopy could tell you that answer. So if you wanted to go for thin with that, you can do it.
The first thing you said was you needed bigger. Say.
Oh, maybe one could even call it the 30-meter telescope. Right. So there's still the hope that planets in and near the habitable zones of these M-dwarf type stars have atmospheres, and we would like to probe the atmospheres. That's very difficult for JWST to do. In a few cases, it could do it, but not for a large number. The ELTs have the potential for doing that with high-resolution spectroscopy. So that's really exciting. We also need to find more of these planets. So as annoying as intensive radial velocity observations are and how much time they take up, we should build radial velocity instruments for the next generation of large telescopes. We've built them for the 8 and 10 meter class telescopes. This kind of result says that we're making hay out of that time, that we can push the precision to even higher levels. We can find smaller and smaller planets. We can do it around nearby stars that you know the name of. We should definitely do this around with the ELTs as well.
I want to ask the next question.
I'm not going to tell you which no.
So earlier you showed the for M-dwarf planets and favored the Gaussian distribution. I wonder if you can.
Probably can, but stars only vary in metallicity by like a factor of 2. So I don't know what that would do here, but protoplanetary disk mass, I think, scale faster than that with stellar mass. So I'm not sure that factor of 2 would make a bunch of a difference, but that's a good question that I hadn't thought of. Well, we haven't found any atmospheres, so no, but there are close-in extrasolar planets that have been observed to be disintegrating. They're so close to their star that they're falling apart and there are extended dust trails coming from the planets. And so that actually gives the opportunity to study in detail the chemical composition of the material that makes it up with spectroscopy. Right. No, and I think because the dominant factor is space weathering, which just takes everything and makes it dark. So I think if the first order thing that we'll be able to constrain by measuring albedos at bare surfaces is space weathering, timescale, and processes. Yeah, I think that's the strongest factor, unfortunately.
All right, we have a lot of
Thank you.